Hey guys, welcome to my YouTube channel. Today I want to discuss the hybrid resonances, and the idea of hybrid resonances is based on the motion of electrons, and electrons actually move in molecules that have a stable, not unstable reacting electrons, like the pi bonds. So the idea of a motion of electron, if you have charge somewhere, negative charge, that's where you start. Or if you have a lone pair, that's where you start. And then the conduits or the river through which these electrons flow are the double bond or the triple bonds. And then they move on to something that is positive and make it neutral, or if it's neutral, they move on and make it negative. Okay, so that's how it goes. If a negative charge leaves a place, the starting place, it makes it neutral. If it leaves, if it's a lone pair, so a neutral atom is losing its lone pair, that becomes positive. Okay, so that's about that motion. Let's go to some simple molecules, see what happens. The idea for CO3 double minus, we know that the structure is like this. This is our Lewis structure, and in our Lewis structure we kind of notice that we have two negative charges, okay, CO2 double negative. These negative charges can move where we have a conduit. Okay, now let's use another color, show you how it's done. The negative charge can move to this place, okay, between the bonds of the carbon and oxygen, literally knocking up the double bond from the carbon, opening it up in this oxygen. So it looks like this negative charge is actually migrating all the way to the one on the top. Okay, if the negative charge or these two electrons come here, they would form a double bond. This double bond would be broken, so you would have just a single bond, and two electrons in this would go on the top into the oxygen, so that would be a negative oxygen. So that is one of the consequences of doing so. So let's just do the connectivities. If I just do this that I just explained with the arrows, it would be a double bond here. These two would be go up as a two electrons, so O negative, and this would remain intact. So that's another resonance form for that molecule. Or you could assume the same exact story that I just told with this part of the molecule with the other part of the molecule, okay, because we have two negative charges, so two places are where I can start running my electrons. So that would be also a third form. In that I would have this negative charge being the spectator, and this negative charge moving here, forming a double bond, while leaving the oxygen as neutral, and kicking off that double bond, putting it as two electrons on the top, so leaving this thing as a single bond instead of a double one. So that's a third resonance form. And if you now look at my three structures, you kind of notice that it's as if my double bond is kind of rotating between the three carbons, between this one, and this one. So you could see that these are called the resonance forms. And if we want to represent all of them, now all of them are a representation of the molecule. The carbonate ion is none of them, and all of them at the same place. So these are called the resonance forms. And then there is a hybrid resonance that I want to start drawing here in blue. That's the kind of structure that we are interested in. Let me just get a little bit of space here. Let's just get rid of the resonance forms for a second. I do the connectivities. Let me very quickly do the resonance form in a smaller fashion here. One with O negatives on this side, one with O negatives down, and one with O negatives on the left side. my bad, the O double bond. So O double bond on the right, O double bond on the left, and O double bond on the top. These are the three resonance forms. When I do the hybrid resonance that I'm doing here in blue, I look at one of these bonds. Now, hybrid resonance, there are two most important things. Hybrid resonance is a kind of a symmetrical structure. So if you find something like with three oxygens in the three sides in a trigonal planar fashion, you could make sure that the bonding order and the charge of all the three oxygens are going to be the same. So if I work it for this one and this oxygen, I could actually expand it to all the other oxygens of the remaining two oxygens. So let's focus on this one. The bonding order, it's a single bond here, a single bond here, but a double bond here. So you could see that the structure is flipping between a single and a double bond. So it's every time you look at it, there's a single bond, sometimes there is a second bond. That second bond, we kind of do it in a dot manner to show that it's not always there. You could look and there is a single bond in this form. Sometimes when you look, there is a double bond. So you can't say it's always a single or always a double. It's flipping between the two. That's the exact same story for the oxygen on the top and for this carbon oxygen bond in the bottom, in this, like in the right part of the molecule. What about the charges? Well, the carbon always stays with no charge, but if we look at this oxygen, we're going to also average the charge. There is a negative charge here, another negative charge, and no charge here. So -2 overall, the sum of those charges divided by 1, 2, 3, three resonance forms. So the charge on the average charge on each of those oxygens would be -2 over 3. And the sum of the charges, because the molecule is CO3 double minus, sum of the partial charges must be exactly equal to the charges of each resonance form and the charge of the ion species itself. So carbonate should have two charges, 3 times -2 over 3. That's going to be exactly -2 charges. Okay, I did this example carefully. I want to move on a little bit faster with other structures, doing ample examples so you could get the hang of doing resonance structure. Now I told you the resonance structure may start with a negative charge or a lone pair. I want to do an example with a lone pair here with this structure. Let's do the NH3 form. This is called goadinium ion. My bad. NH2 double bond carbon, NH2, NH2. This is positive. Okay, so there's a lone pair here, also a lone pair here. I could start with each of these lone pairs moving towards the top, like this one going here, knocking off this double bond to actually neutralize that positive charge. Okay, and that would give me, this one is just watching, this one becomes NH2 with a double bond, it becomes positive because it was neutral, and this, that what used to be neutral, that what used to be positive, receives these two electrons from the double bonds and becomes neutral. You could do the exact same story with that one over there. I would like to show it in red. If you do that, you would have this third structure where your right side nitrogen will become the one that is positive. Okay, so those are the possible three structures for this one. You could now draw the resonance form. Okay, like this. If I look at this nitrogen on all the three molecules, three resonance form, there is a positive charge, 0 and 0, so +1 over the 3 resonance form, a third positive on all the three, and then you could see there is a double, a single, a single. Remember, we just focus on one of them and then we expand it to the others because we know it should be, how to say, symmetrical. Hybrid resonance should be symmetrical. So going between a double and two single, between single and double, that's partial for after a single bond, okay, after the connectivity, because you could have a double bond sometimes if you look at this form, for example, over here. That's this. Let's move on to yet another example. Also, some molecules have no charges, but they could still run down the electrons because of what we call, they have conjugation. Benzene molecule is a good example of that. If you have CH, C6HX, you would have this sort of structure, and that's alternating single and double bonds. Though you have no charge to start it, but because it could start in a circle, like in a loop, this could feed. You could actually broke this double bond here, move it to this part, broke this one, move it to this part. This becomes positive when you do so, and because it's a loop, this can now go and cancel up that positive charge when you open up the third one and complete the loop and actually put these two electrons on the previously, while leaving this positive, previously being positive carbon, after leaving this, it becomes satisfied with these two electrons and becomes neutral one more time. So that would also be this becomes a double bond, this becomes a double bond, and also this becomes a double bond, and all the ones that used to be, all the three that used to be double bonds are now single bonds here. So that's a second resonance. If you repeat that, you will get the first resonance form. So there are two resonance forms, the hybrid resonance. There's also a tendency not to draw all the carbon hydrogens and show just the carbons in sort of a hexagonal form, to make sure that we don't waste the time. I'll use this convection. For all the carbons with hydrogens attached to them, I'll just do a dot. So 1, 2, 3, 6 carbons, I do this, and then if we focus on any of those bonds, like this one for example, it goes between a single and a double, so you could do this, okay? Or they do a circle because it's kind of harder to do this for all of them, but literally it's this one, but it's easier to do a circle. Sometimes they even do a full circle to represent the benzene molecule. Like remember, C6H6 is the benzene molecule. If you have that molecule, two hybrid resonances for any benzene ring, it could be this or this, the alternating double bond, and the resonance form is kind of like that. There's no charge and no actually other things to worry about. You could always do partial sync as we're doing the partial, but in organic chemistry books it's just a full circle representing your chemistry of benzene. Let's move on to yet another example. Now if we have a dative bond in a molecule and we want to do resonance form like N2O2, like N2O, that's the structure for N2O, and if you're interested to do that, the dative bond, I'm going to actually let you know what convention to use. One convention is to replace the double bond with a single bond, and where the head of the arrow is, you put a negative, and when the tail of the arrow, you put the positive, or replace the dative bond with a double bond literally, okay? The top one is called ORFC, meaning octet root formal charge. These are called formal charges. And the other one is called BDFC, which means best distribution formal charges, which simply means that you add a double bond to make sure that the formal charges is being best or ideally distributed. Let's see how much time we have. Still a lot of time, so let's just go and convert this based on ORFC and try to do the resonance form. I'll do the, so you can't use the Lewis structure as one of the resonance form if there is a dative bond. I should give you one of these two convections to choose from, and then you could actually make your first resonance form. So for this one with ORFC, I just do nitrogen, nitrogen, and I replace that dative bond with a single bond and then do positive or negative. Okay, now I could start from where I have negative charge, and I could do this. My bad. So I could do this. Once I do that, I have literally moved this negative charge. This becomes a double bond, and I have broken this bond and moved the 2 electrons to this nitrogen, so this becomes negative. The nitrogen in the center remains positive because it's receiving and donating electrons, so it's kind of a dealer. It just takes it from you and give it to somebody else, so it's not changing any state in its charge. The resonance form, so there are 2 of them, and the hybrid resonance should then be, and now because there are 2 different atoms, we have to actually separately analyze them. The central nitrogen is just positive, or you could just say positive 1, positive 2, positive 2 divided by 2, it's positive. My idea is to say it's not changing, so it remains n positive. For this negative oxygen, there's negative 1 and 0 plus negative 1 over 2 resonance form, so half negative. Also here there's negative 1 and 0, again 1 minus 1 over 2, so it's half negative charge. And then for the partial bonding, it's a single and a double, so it's like this, but this guy is a double and a triple, so it's like always you look at it, it's going to be a double bond. Sometimes it's a triple bond, so sometimes there's means that you do dotted. Okay, that's the sort of the hybrid resonance for this molecule if you wish, and you could check the charge is going to be 0, as is the charge for N2O molecule. There's no charge. And also in here you could see that the overall charge, a positive and negative, cancel out to give you a neutral N2O. Let's now move on to yet another example. Let me check my list. Okay, we're doing good so far, or at least so far so good. Let's do one of these examples as we wish to do. Let's do ClO4 minus. ClO4 minus, we all know that this is the Lewis structure for it. There's a chlorine O negative becomes satisfied, so we could actually donate all those lone pairs to the remaining oxygen to make a tetrahedral framework and a ClO4 negative. And let's do BDFC on it, and that means doing double bonds for all the datives and then try to have the first resonance form. That's the first one. You could have this negative charge moving to the center, and there are 3 passes to continue from there, either on this bond, on this bond, or on this bond. Let's do it on this one, and then I repeat it on the second and on the third one as well. As you do so, you make the oxygen being neutral and also a double bond here, and you met the terminal carbon, whether if it's this or this or this, becomes negative, and the double bond goes away, so you remain as a negative. Let's just do the that's 1. That's if you do with this one, and if you do with the one on the top, you will get the O negative on the top. So that's how you do the four resonance form. If I just get rid of those, I could now do the hybrid resonance for the four resonance form that I have, and that would be the Thiel O. Let's get rid of this structure on the top, the least structure, to make more space for myself. Make sure you guys can all see it. Okay, that's it. Now I go to focus on one of these bonds and the charge, and that would be the same for all the others, because the all oxygens in the hybrid resonance have the promise of being symmetrical. So it's a double, a double, a double, and a single. It's going between a double and a single bond. Anytime you look at it, it would be a single. Sometimes it's just a double bond. So, and that's the same story for all the rest of the oxygens. And for the charges, 0, 0, 0, and -1, so -1 overall, divided by 4 resonance structures, that's -1/4. So you do -1/4, -1/4, -1/4, -1/4, 4 of a quarter negative charges. That's equal to -1 overall, and that's the charge for ClO4 negative. That's the hybrid resonance for this onion. Let's move on to yet another example. So for this example, I want to do, let's see, CH2 and N and negative and positive. Okay, there's no resonance, there's no negative bond, so I could just use this, and I could move on this negative charge down here and move this one down here. Okay, that would give me N triple bond N, C single bond, because this charge have moved, and CH2 negative. Okay, now CH2 negative goes on the top. I just wanted to say carbon, not the hydrogens are negative. Okay, there I could do nothing more. If I just go back and move the negative charge, I would get that other resonance, the first resonance form. So those are only two. There are only two resonance forms, and I'm going to do the hybrid resonance in this color. Just the connectivities. Let's just move down here so that we could have more space. Okay, so if we now concentrate on this one, we could say what is the charge, and we then concentrate on that nitrogen, and the nitrogen on the center. The nitrogen on the center is going between a net positive and neutral, so it's 1/2, positive 1/2. This guy between a neutral and a negative, so negative 1/2. Also a negative and neutral, again negative 1/2. My bad. Here, when you do that, the charge on the nitrogen never changes. So you have positive 1. Actually, positive, positive, positive 2/2. That's positive 1. I apologize for that. Let's go back to the bonding. First, look at this bond, a single and a double. So it's always a single, sometimes a double. So this is this. And this goes between a triple and a double, so always it's a double bond. Sometimes when you look at it, my bad. Sometimes when you look at it, it's a triple bond. So that's how I show this one. That's the hybrid resonance for that sort of a structure. Let's move on to yet another. So two resonance form, and if you check, the charge is just 0, and you could also see CH2 and plus and negative. The charge is 0. The formula for this molecule is CH2N2. Okay, and the charge is just 0. It's called azometan. So we talked about azomethane molecule, the CH2N2, and now we're going to move on to yet another example, and that's this molecule. a negative charge and two double bonds. Remember how we talked about benzene molecule, where you have a CH, 6 CHs. We just showed them with with dots. Here I have done that to make it simpler on myself, and I want to talk about what happens in this molecule. That's one of the resonance form. I could move it in a loop. Okay, this bond negative charge could come here, and the bond could open up on that side of the pentagon, or on that on that corner of the pentagon. So I could have the pentagon being negative on that corner. Oh, my bad. Being negative on that corner, and here's a double bond that I have formed. I could also do the exact same thing, continuing to do that. This comes here, and this double bonds open up and goes to this corner. So we could also have this corner of the pentagon being negative. This would be a double bond. Also on the top there would be a double bond. So there are two different locations, and if you look, it's every other adjacent carbon or alternating carbons. The negative charge from the very beginning, I could judge that the negative charge is here. It could also be not this one, but here. It could also be on this one, or it could be on this one. Okay, so alternating atoms are starting from that corner. Let's see. Now if I do from the other part, I could actually do this. And that would be this carbon now. And I could also continue doing this if I open up this on the other end of this and make this one land on this carbon. So literally every corner can have that kind of negative charge. So you could have negative charge on every corner of this pentagon. If I do the hybrid resonance, that would be minus 1 over 5, minus 1 over 5, minus 1 over 5, minus 1 over 5, minus 1 over 5. That's how you do it. Okay, or you could just say one negative charge in all of the center, and then it means it's rotating on all the carbons. So that's how you do this for this molecule, the hybrid resonance form. Let's do yet another example. And then we could actually finish that up with this example. Let's see how much time we have. There's still a little bit time. Let's talk about ClO2 minus. ClO2 minus, if we look, that's the structure, O minus, and we have to do this with O, the dative bond. We have to do BDFC, or we will be given to do BDFC. So we kind of do replace the dative bond with a double bond. And we could see there's a motion of electrons from here, and that would give us O chargeless, a double bond, and Cl single bond because the bond has opened up, and O negative. That's the two resonance form. If you play with this, you'll get the same exact resonance structure that you just have. So this is this. If I look on this oxygen, it's -1 and 0, so -1 over 2, -1 over 2. And if we look at this bond, a double bond and a single bond, so it's like this, also the same exact thing here for the other one. So that's the, oh my bad, you can see this -1/2 here, also -1/2 here. Okay, and let's just paint this in a way so everybody could see. Let me just check. Yeah. Okay, so I want to wrap it up here, not making the video very lengthy. We will talk and more about hybrid resonances of different, more complex structure as we come back. Okay, Let's wrap it up here for today.